Our only natural satellite serves as the closest celestial body to Earth and acts as its permanent cosmic companion. Likely, the Moon formed from a powerful collision of our planet with an object the size of Mars. This happened billions of years ago. The impact melted Earth's surface, ejecting a massive fragment of matter into near-Earth space, which cooled and took a spherical shape. Now this crater-covered sphere orbits our planet, causing ocean tides. The Moon's diameter is about a quarter of Earth's, placing it fifth among the largest natural satellites in the solar system. The Moon's phases include new moon, full moon, crescent stage, as well as first and last quarters. In any phase, our satellite is easily distinguishable among other objects in the night sky, and sometimes even in the daytime. Imagine, you wake up at night and notice that the Moon looks brighter and larger. In a sleepy state, this might not catch your attention. You fall asleep again, unaware that Mercury has taken its place. Mercury's surface, the planet closest to the Sun, resembles the lunar one. It is dotted with meteorite traces. Mercury's size is less than half of Earth's, but it is larger than the Moon, which would intensify its influence on our planet. Nights would become brighter, tides and add stronger. The duration of the lunar month, the period for the satellite here Mercury to pass through all phases, would shorten by 14 hours. However, such a substitution would not radically change Earth's conditions. And what about Venus? Suppose, instead of the familiar satellite, the sky was adorned by the third brightest natural celestial object after the Sun and the Moon. Venus is called the Earth's sister due to nearly identical mass and size. In Earth's sky, it would appear as large as Earth from the Moon for the Apollo astronauts. Venus would shine much brighter than the Moon. Firstly, it reflects sunlight 6 times better. Secondly, it would occupy at least 16 times more space in the sky. Therefore, Earth's nights would become as bright as early twilight. When observing Venus, one could see blurred spiral patterns on its yellowish-creamy clouds. Venus would not become Earth's satellite. Rather, both planets would orbit around a common center of mass, forming an unusual orbital system. If Venus moved at lunar speed, a collision between the planets would become inevitable in the near future. Let's continue the reflections. If Mars replaced the Moon, it would immediately catch the eye due to its reddish disk and sizes twice those of the Moon. Without a telescope, one could discern the unusual color and dark areas on the surface. Even ignoring the red planet, the consequences would be felt immediately. Mars is half the size of Earth but many times larger than the Moon. Replacing a small satellite with a larger one would disrupt the delicate balance. In the worst scenario, if Mars appeared while you were by the sea, urgent evacuation would be needed. Its gravity would cause giant waves, like huge tsunamis, crashing onto the shore. Mars would reflect sunlight stronger than the Moon, making nights brighter. Earth's landscapes would acquire an ominous red tint. On the other hand, through a telescope, one could admire Olympus, the highest mountain in the solar system. Mars is not massive enough to sharply change Earth's orbit, but over time, the planets would begin to orbit each other, forming a binary system. Since Mars would seem so close, interplanetary flights would become a reality. Let's move to more large-scale ideas. If Jupiter replaced the Moon, Earth would lose its status as an independent planet and become a satellite of the largest giant in the solar system. But there would be positives. The sky would become incredibly beautiful. Jupiter is enormous compared to the Moon, and its striped sphere would stretch across the entire horizon. One could observe yellow, brown, red, and white clouds in its atmosphere, if there was enough time. Unfortunately, the gas giant's gravity would immediately cause earthquakes, volcanism, and tsunamis. Earth's crust and mantle would be pulled toward Jupiter, leading to the planet's destruction. Earth would be stretched and compressed by 90 meters in different directions. Alas, Earth's speed is only a tenth of what's needed for an orbit around Jupiter. Therefore, in less than a day, our planet would collide with the giant. Let's distract from gloomy pictures. Replacing the Moon with Saturn would create an unforgettable spectacle. The planet is 35 times larger than our satellite. The golden sphere would occupy 18 angular degrees of the sky, and the famous rings would stretch from horizon to horizon. Earth would be farther from Saturn than its satellite by mass. Since Saturn is much more massive, Earth would become its satellite. Unfortunately, Earth's speed wouldn't suffice, and a collision would occur in a few days. But before entering the atmosphere, one would have to pass through the stunning rings, consisting of debris from comets, asteroids, and destroy moons. This would be dangerous. Don't forget about Saturn's 53 satellites, which would need to be navigated around. Suppose collisions were avoided, and Earth became the 54th satellite, then the giant's gravity would cause global tectonic shifts. The crust would tear apart, leading to complete destruction. Again, not the best outcome. Uranus and Neptune are ice giants. They are similar in size, larger than Earth but smaller than Saturn and Jupiter. Both are covered in ice and have a greenish-gray color. The consequences of replacing the Moon with either would be similar. Let's choose at random. So, imagine Neptune in the Moon's place. It is 14 times larger. The planet would appear as a huge bright blue ball day and night. Neptune would look 15 times larger than the Sun, causing frequent eclipses. After the Sun hides behind Neptune, Earth would plunge into darkness for an hour and a half. Neptune's mass is 17 times greater than Earth's, its gravity stronger. Earth would become its satellite. Again, it would orbit farther than Triton, Neptune's largest satellite. In such conditions, the risk of collision with Triton would be high. But even without encounters with moons, there would be plenty of problems. Waves would become 1,000 times stronger than lunar ones. Neptune's gravity wouldn't tear Earth apart, but would heat it. Seismicity would intensify, causing earthquakes and volcanoes. Possibly, the internet would shut down. Imagine two parallel horizontal lines. Connect them at random points in two ways, with a vertical line upward from the bottom to the top, and with a diagonal one. Which is shorter? Of course, the vertical. This is the shortest path between the lines. And this is the key answer. It's better and faster to reach orbit via straight trajectory. The bottom line is Earth's surface. Our planet is a complex mixture of substances gathered into a mass of about 6 sextillion tons. That's 6,000 billion billions. Essentially, a bunch of zeros. This mass acts like a huge magnet, holding, among other things, the atmosphere. The top line is the atmosphere's boundary. Above is orbit and space. But the atmosphere also consists of matter, gases with density. During a shuttle launch, gases press on it, create friction, and slow it down. Movement in vacuum is like through air, but in the atmosphere, like through jelly, grape, or strawberry. A lot of energy is needed to overcome this, plus the gravity of the giant magnet, Earth. Airplanes suffer less from the atmosphere, using its density for takeoff and flight. They are helped by engine thrust and wing shape. Wings divide the air into two streams. The streams want to merge behind the wing, but the shape forces the upper one to move faster. Faster movement means less density. The lower stream is denser than the upper, creating lift. Wings allow the airplane to glide through the air. Of course, without a force pushing forward, this is impossible. That's why thrust is needed. An airplane requires high speed for takeoff, from 96.5 kilometers per hour for light ones to 241 kilometers per hour for liners. A Boeing 747 needs less than 3 tons of fuel for takeoff and climbing to 3 kilometers. Impressive. But compare it to the shuttle. First, the shuttle's small. Short wings are noticeable, useless for horizontal takeoff. Large wings aren't needed in vacuum and would be fragile during launch. Small wings are only for landing, so the shuttle doesn't spin during descent and returns to Earth without engines. The shuttle's engines differ from airplane ones. Airplanes need air to work. Shuttles don't, as there's little air in space. Therefore, rocket engines are used. To understand, inflate a balloon and release it. It will fly in the direction opposite to the escaping air. For takeoff, a rocket must create thrust and burn fuel. The shuttle can't do it with just 3 engines. It needs 2 solid fuel boosters and a large tank, jettisoned later. The shuttle reaches orbit only with sufficient power. With 3 engines and boosters, the thrust is 3.5 million kilograms. The external tank holds 725,000 kilograms of fuel. These engines are very complex for control. Can the shuttle be modified for launch like an airplane? No, it would require even more fuel for speed on a diagonal trajectory. Even in the upper atmosphere, gravity won't release it. To exit the atmosphere, an object needs escape velocity to overcome gravity and reach orbit. Orbital speed is 28,000 kilometers per hour, much higher than sonic and a liner's cruising speed. Imagine an airplane at that speed. How much fuel, plus strength to not fall apart, cost and technology. Fantastic. Shuttles are becoming obsolete, so scientists are seeking new ways to orbit and space. One idea is a space elevator, a tower to a geostationary satellite orbiting with Earth. Height minus 35,400 kilometers, Material: carbon nanotubes. Super strong. The platform in the tower moves electromagnetically. The trip from Earth to the satellite is 5 hours. This would make space faster and safer, but nanotubes aren't strong enough. The search for material continues. Another idea is the space tram, smaller but still huge. A vertical vacuum tunnel pushing the shuttle on magnetic levitation. No air means no drag. Electromagnets accelerate to near-orbital speed. The shuttle is lighter, without extra fuel, but how would the crew withstand the acceleration? They might get flattened. If this seems strange, and it is, here's the final idea: use airplanes for orbit. Not a joke. The airplane won't reach space itself, it will serve as a platform. A special airplane with a 122 meters wingspan will climb above 10 kilometers. A shuttle launched from it will pass through less atmosphere, easier overcoming gravity. Richard Branson is developing this in Virgin Galactic for space tourism.